about AlphaFold now, which is probably one of the most exciting things I think that has come for protein design in a little while, or for protein prediction in quite a while. We've seen a lot of progress since then, but AlphaFold was really, I do believe it was a breakthrough. But we would have got there eventually. So DeepMind, yeah, they get credit, but not all. So yeah, when we last left off talking about CAS, we had seen some good progress over the years. AlphaFold1 and CAS 13 made a pretty good improvement for some of these difficult targets. But now we're entering CAS 14. It's 2018 now. A little bit of context. Some models have started to come out that are end-to-end. So you give it a sequence and it'll predict full atomic structure. Those have started to pop up now. And this is, I think, one of the first, this might be the first CAS where they really started to be, like compete. So AlphaFold, when it released, really blew everybody else out of the water. You see that? Okay, so this is median C alpha RMSD. All the other competitors, as we saw, they were making progress. Everybody was improving and we were getting better. The median RMSD is around 3 or so, maybe slightly below 3 angstroms. But AlphaFold came in and really changed the game, brought it down to about an angstrom RMSD, which is really impressive. And as we can see, they also have some really good structures. These are some of the ones I highlighted, but you can see the termini are a little less well predicted, but for the most part, everything is pretty identical to the native. Really high TM scores, low RMSD. This model also does not explicitly model other molecules. So here we can still see it recapitulating a native site for this metal ion, for the zinc actually. And you can see that the side chains are placed such that it would still coordinate the zinc, even though it's not modeling the zinc. So it's learned that some of these sequence patterns can accommodate other molecules, or that they're crystallized with other molecules, even though it's not explicitly modeling that. It can also work for really large structures here, where it's mostly correct. There's a few mistakes, mostly in the loopy regions and in some of these like outer regions, but still RMSD of 2.2, really high TM score, really good prediction overall. 2018 is when this model debuted, but the paper wasn't released until 2021, and that's about when the full open source code was released. But in that gap, we did see a lot of progress. There were a lot of attempts to recreate the performance that AlphaFold displayed in CAS 14. That's where we saw Rosetta Fold come out. Rosetta Fold didn't do quite as good as this AlphaFold2, but it still made a dramatic improvement, and some of the ideas that Rosetta Fold2 came up with are still being employed in like ARC Diffusion and ARC Rosetta Fold2, etc. Okay, I have this one slide about the differences between AlphaFold and OpenFold, and it's one slide because there's not really any differences. The main idea is that AlphaFold2 was released only for inference code, so you can't reproduce the training of AlphaFold2. So Mohammed Al-Quraishi and some others got together and it's like, hey, we can do this. They published a really nice, detailed algorithm in their supplemental material. So they decided to get together and try to recreate AlphaFold2, and they open sourced the code and made it completely trainable for other people too. Some of the major benefits that they've done when they did this was a lot of optimization. So they introduced custom kernels and some other optimization tricks, like faster attention. And because of that, it runs 3 to 5 times faster than the original model for most proteins. It also uses less memory, so you can cram larger proteins into the same GPU. It's also implemented in PyTorch, which is the most widely used machine learning framework, whereas AlphaFold2 used JAX, which is more Google's newer experimental-ish framework. But it also can use TPUs, which is different. And OpenFold's paper was recently published this year, and they show some really cool experimental things like that, so it's a really good read if you do want to read that. Okay, let's talk about the model. Oh,
You said OpenFold runs 3 to 5 times faster on what proteins?
Yeah.
Which proteins are those?
I don't know. I think it's mostly like the larger proteins that AlphaFold, AlphaFold, I think it's the larger ones where the GPU memory is running into an issue. Also, it's with the scales cubically with protein length, so there's something with that.
Something like that.
Yeah.
Okay.
Okay, cool. So let's talk about the overview for AlphaFold2. Like we mentioned, structure prediction is really taking a protein sequence and then trying to get the structure for it. AlphaFold does this by taking the sequence and then performing database searches. So first, it takes the protein sequence and compares it to a big, gigantic database of sequences coming from a variety of different species, and tries to find sequences that have high sequence similarity to that to your query sequence. This forms the MSA. We'll see an example of that in the activity, but essentially it's just homologous sequences that are similar to your query. We also do a structure database search. Here they take the protein sequence, your query sequence, and align it to all of the sequences of structures in the PDB. Once they have found sequences that are similar to the query, they go and grab that structure from the PDB and then use that as a template. So that will form the basis of the inputs. We have an MSA, we have a sequence, and then we have templates. These all enter the model, some black box neural network for now, and then it comes out into a full 3D structure with confidence values. So here we have the model colored based on its PLDDT confidence value. The red regions, or the orangish regions, are the less confident regions, at least in this picture. And then the dark blue are the really confident regions. So as you can see, the more domain-esque areas that are more well-defined have really high confidence values. And then the more loopy regions here, and then like the termini regions, are a lot less confident because those are more flexible inherently. We also see another form of a confidence here. This is the predicted aligned error. This is a pairwise matrix of error, essentially estimated distance, how far they are off from the native. So we have both the number of residues and the number of residues, and it's a pairwise. Every residue pair has a different estimated error value. We'll go all over that a lot more in detail, but are there any questions on the overall inputs and outputs of the model?
Just a short question, because sometimes in AlphaFold2, for example, I work with GPCRs and I want to predict inactive form. I can theoretically take the structures from database, which are structures from PDB, which are just inactive, and give it as an input, right?
You can do that, but I'm not sure it'll listen to those input structures. We'll see some of this later, but AlphaFold doesn't always listen to its templates. The MSA is the biggest factor for the inputs for AlphaFold2. And by modifying the MSA itself, you can create different conformational states that AlphaFold will predict. Whether they're realistic is still to be determined, but you can bias it towards different conformations by affecting the MSA. And we'll see that a little bit later too.
I'm gonna add something onto that. So sometimes AlphaFold learns something about a particular protein so strongly, especially for ones that have different conformation states, that despite the MSA being primed for one state, like state B, giving it a template, there have been papers that found, like in recycle 1, let's say it predicted something that was close to the conformation you were looking for, but then the weights corrected it in following recycles to bring out state A, which is what it saw in its training data set for that sequence. So sometimes it'll override everything you give it, depending on how strongly it's learning the signals.
So let's talk a little bit about its performance. We saw that it really shined in CASP 14. Let's break down some of the other, how it did otherwise. So this is a fraction of all proteins in its test set, and this is the full chain C alpha RMSD. So as you can see, most of the time it is predicting structures that have low C alpha RMSD. However, there are definitely a tail over here that's quite large for structures that it's just getting wrong, pretty much. This is just over 8 angstrom RMSD, which can be quite bad. But for it's length dependent, so it's hard to say exactly how bad that is without knowing the context of how big the protein was. But it's still doing really good for most proteins, which is cool to see. Did you have a question?
Yeah, so for residues it does poorly on. Are those like inflexible like chains, or is it like really like helixes and like four parts of the protein that shouldn't be predicted, like that are probably have strong static structure?
It's usually the loopy regions. The second plot shows its sidechain prediction capabilities. So this is the fraction of correct chi1 rotamers. So chi1 is one of the dihedral angles that you can use to parameterize a sidechain. Most residues have more than one chi-angle, but chi1 is still relevant for all amino acids except for glycine and alanine. So it's still a useful thing to look at. But on the x-axis, we have the LDDTC alpha of a residue. So this is measuring the local prediction quality around each residue. As the local quality increases, it's getting more and more accurate about how to predict that sidechain. So that kind of makes more sense. That kind of makes sense, right? If you're getting more and more confident about what the overall structure is of the domain itself, of the backbone structure of the protein, you should be more able to predict the correct chi-angle, the correct placement for the sidechain. So that is cool to see that it is also growing. Okay. Like I said, AlphaFold also predicts its own confidence value. So one of the cool things to look at is how well does that confidence value actually calibrated? So how good does it agree with the true value that it's trying to estimate? So as you can see from both of these plots, first one is the LDDT versus PLDDT, and then this is TM score versus PTM score. As you can see, there's pretty good agreement between the predicted confidence value and the true value, which means that it's a fairly reliable estimate of how confident the model is and how good your prediction is, which is useful for actually using these models. So yeah, as you can see, it's not perfect, but pretty reliable. So that'll be useful for us as well. One of the important things to look at is how the model is using the MSA. So here on the x-axis, we have the number of N effective. So this is the number of sequences in the MSA for each chain. And as you can see, if we have, so this is 10 to the 0, so that's one sequence. The performance is drastically different if you have a bunch of sequences in your MSA. So here is 10,000 sequences. So adding more sequences to the MSA really improves, but it starts kind of plateauing maybe around 30 so sequences, which is kind of cool to see. So maybe there's not much more information you can glean from the MSA after past 30 sequences, but there could still be some. As you can see, it still kind of increases as it goes. So MSA is super important for getting accurate predictions. If you have one sequence, you have dramatically lower performance. So that's one especially thing to keep in mind, especially for de novo design, because de novo design, a lot of the time you're trying to create a protein from scratch. So it might not have a lot of evolutionary history, or it probably has no evolutionary history, or it might not even be similar to proteins that we know of that we have access to already. So that can really dramatically affect the prediction quality.
So we can run it with 0 sequences, right?
Well, no,
No.
because you have the query sequence, so that counts as one.
Okay. Yeah.
Yeah. They also did a bunch of other ablation studies where they removed components of their model to try to understand how big of an effect it has on this prediction. So they tried a bunch of different things, first of which they had self-distillation, where they made a bunch of predictions with their model and then fine-tuned their model on the high confidence predictions, which is a way of just kind of bootstrapping more data for their model. Because there's only so many structures in the BDB, there's like maybe 200,000 structures. If we talk about unique structures, it's even lower. So the model itself is very data limited. So this is one way of kind of bootstrapping and getting more data into the model so it can try to learn more. And by training on the high confidence models, it was able to kind of extract even more data because it's able to improve the GPT by roughly 2%. It's hard to exactly say, but it is over the baseline model. We can see that removing templates has very little effect on the overquality of the predictions, suggesting that the model doesn't really look at the templates a lot. And something we'll talk about later is they actually trained 5 different models, 3 of which use no templates at all. So it's not even like it thinks about the templates, but not much. Yeah, so they do a bunch of other ones. I think some of the interesting ones are the recycling. So the model makes a prediction. They give them that prediction back to the model and tell it to try again. They do that 3 times, and that also improves the performance. So kind of giving the model multiple chances to make a prediction is beneficial. And yeah, they do a bunch of other things too. But those are the main ones I was talking about. Yeah.
Is there any way with AlphaFold or OpenFold or any other structure prediction methods to more heavily grade templates?
Theoretically, Rosetta Fold, but we haven't really gotten that to work before. Right, Amrita?
Sorry, what was the question?
Getting them to pay more attention to the templates. Rosetta Fold technically has like this knob you can turn to say how confident you are about this template, but it didn't really seem to work in our hands. I don't know.
It doesn't really scale linearly with the template confidence. Yeah, it doesn't seem like any of these models is trained to have to follow the template that we give it, and so a lot of times it's more focused on like getting a good prediction rather than following the templates, and that, I guess.
Yeah.
The other thing you can do is like curate what information you are providing. So if you say don't give it any MSAs, then like its only fallback is kind of
Yeah.
the templates, and so you can kind of pack it that way.
And that only helps sometimes.
Yeah.
Yeah, it's very protein dependent. But you can easily imagine like training a new model, but specifically telling it, I'm giving you the correct structure. Just reproduce that. But also make some other prediction or something like that. You can like tell the you can like train the model to do these tasks, but that's not currently possible with AlphaFold right now.
Do you know how OpenFold works? If OpenFold doesn't use MSA?
It's similar to AFsample, which we'll talk about later tonight. But they work very good. The structure prediction module is different.
The self-distillation trains only taking really high confidence structures?
Yes.
Makes sense.
So I wanted to show this video, which I thought is pretty fun. So the idea here is they have this EvoFormer block, which we'll talk about, that processes the MSA. So essentially this module is looking at the MSA, trying to find patterns of coevolution, where residues might be in contact, stuff like that, based on the sequence, as well as the sequences of other species. What they've done here is they've trained a model, a structure prediction. So there's the EvoFormer, and then there's the structure module that makes a prediction based on what the EvoFormer has processed. What they did here was chop up the EvoFormer into smaller segments, and then trained a separate structure prediction module for each of those small chopped up pieces of the EvoFormer. So the idea here is, as the EvoFormer gets deeper, it gets a more refined idea of what the protein looks like. And so hopefully here we should see the predictions get better and better as we add more and more EvoFormer layers, processing more and more information from the MSA and from the sequence itself. And to see, but as you can see, some of the structures it defines really quickly. Like this green region here is only really well defined, while it's still figuring out what to do with some of these other regions. So it does have like some concept of what it wants out of this protein. It may take a little while to like get that final structure out of it. But yeah, also like, what are these doing? These aren't really doing much. So maybe like you could stop this prediction early, maybe. There's some like interesting things to maybe poke around at there. But I think that's a fun video to look at anyway. Yeah.
So I've heard of recycling iterations, but I've never really seen the word block. What's that used in context of the video?
Yeah, so that's what I was trying to refer to when I said it was cutting up the EvoFormer.
Oh.
So they have 48 layers or blocks of the EvoFormer, and here they trained on just the first one or the first two, the first three, etc., all the way up to the full model size.
Okay. And so then, is the recycle just meaning taking that 48 block and re-inputting it?
Yep.
I mean, it'd be great.
Pretty much. Okay, let's open it up. So this is really the high-level overview of what AlphaFold actually looks like. Like I said, it takes an input sequence, does some genetic searches, so it searches a bunch of sequence databases to try to find homologous sequences. It also searches the PDB sequences to try to find homologous structures. These structures make up the templates, and these sequences coming from here make up the MSA. You can see that maybe there are some differences between the human, the fish, the rabbit, etc. Those are just species differences or whatever. And then we also have some templates coming from the structural homologs. Here they convert the structures into these distograms. So they compute the distance between every pair of residues within that protein based on C alpha, or C beta actually. And then they create a distogram here, and they only use 4 templates. So they use templates. That is the input into the model. Then they process, so this creates the MSA representation. So they do some embeddings. So they throw it through some layers to get some sort of meaningful representation that represents what this MSA is. I speak in very abstract terms because that's what it is. We don't really know what's inside of these vectors, but they're high dimensional vectors, 128 dimensions for every pair, or for every position in this MSA. So it's quite a large structure object, but yeah, it represents the MSA in some abstract way.
So it's a 128 by whatever
So it's
depth of your
number of sequences by number of residues
Oh, I see.
by 128.
Oh,
Yes.
oh.
So it's quite a large object. And then we also have this pair representation that represents every interaction between every residue in the protein itself. So this is now number of residues by number of residues by number of channels, which is also 128, I think. So this is also quite a large structure that goes through it. But this is kind of where the model learns to reason about its other residues in the protein. It starts to get some sort of idea of where they are relative to one another, which is how it kind of gets processed into this final structure. So the EvoFormer block is where the whole processing of this MSA happens. It processes both the MSA and the pair representation and updates these iteratively until we have a final version of them that's just really processed. So essentially, we're taking the MSA, trying to extract all the evolutionary information, all of the couplings between the residues, such that they're meaningful for the structure prediction task. And now we have updated representations of both the MSA and the pair representation. We actually throw away the representations for every sequence besides the one we're interested in, which is just that first one, the query. This is now our single representation, which is just a sequence representation. We still have our pair representation. And then both of these come through the structure module block to iteratively create this 3D structure. It does so in a very interesting manner, using each residue as an independent object that can move around relative to one another. So this is called a residue gas. We'll talk about this a little bit later too. But the cool advantage of that is that it breaks a chain structure. So traditionally, you would have to keep these two residues close to each other in 3D space because they're actually peptide bonded. But by breaking that structure, you can simultaneously refine the local environment of each residue, but it may break some physical constraints. So they have a relaxation step at the end to help try to enforce some of those priors. And then it produces the 3D structure as well as the confidences. And then it does recycling. So we have the predicted structure after the first pass, and we go back and we take information from that structure and add it to the MSA representation and to the pair representation, and then process those all over again. So it's taking this prediction, looking at it, trying to identify what it did right, what it did wrong, and then merging that information back into its initial representations of the MSA and the pair, and then process those all over again to try to make another prediction. It'll actually recycle 3 times, so there's 4 passes through the network on a standard run before you get your final prediction. Yeah.
Does it keep all 3 cycles in the MSA, or it just added?
Yeah, so this MSA was pre-computed at the start, right? Then we embed it and get some sort of high-dimensional representation of what this MSA means, and then we do all the processing, get our structure, and then we take information from that structure and just add it to that initial representation. So this representation that they learned from this doesn't really change, but the processing will affect whatever was like added to that structure. So it just like adds extra context about what it thinks the previous prediction did right or wrong.
And it maintains the previous two predictions, I guess, on the third time is what I'm gonna ask.
What do you mean by maintain?
Like is it concatenating the other the MSA that's being recycled back?
It's not concatenating, it's just adding the information to it.
Yeah, so then does it keep that information for the next two cycles? So if you
I
or does it get rid of your first cycle information and
Right.
the second cycle it just replaces that?
Yes,
one?
exactly. That's what's happening. So it doesn't. So this MSA representation doesn't accumulate the knowledge from the previous recycles.
Okay.
It just takes it from the last recycle. I don't know. Does that make sense?
Yeah, okay.
Adding a little bit more context to like the MSA vector and what it actually is basically just the idea that you look at two positions of a residue and you see how much they change over the sequence, and the whole idea is the more two residues are correlated, like if X is every time X changes, Y also changes, it usually implies that they're really close together in 3D space because a protein would need to maintain that interaction. And so if one of the residue identity changed, the other one had to change to maintain that interaction. So whether it became charged, or hydrophobic, X and Y would always change together. So the stronger that correlation is, the stronger the correlation is in structural space. And so you basically rank like, okay, stuff that's closest is going to be the stuff with the highest correlation, and that's how it decides how to make that contact map. So what it's that MSA vector is basically just an idea of this stuff is what's most likely closest in structural space, and then when we add it with the EvoFormer, like the 2D representations and everything, it's getting a very strong idea of what's close together and what's not. And when we actually train this and it becomes like just random numbers, it's just using context from every other protein it's learned to really hone down exactly what the numbers ought to be for that particular protein.
Is there an optimal like MSA diversity? Like,
And that matters a lot.
yeah.
Like if you just take your query sequence and pad it, like take 30 copies of that, you're not going to get any extra information out of that. You do want some diversity, but you also don't want it to be random noise. So like there's been a lot of people looking at like what optimal MSAs look like, and I don't think we have a clear answer yet. But so some diversity is important, but not like random noise diversity. So it's hard to say.
How did the structure the data and then very last step into the previous MSA?
Yeah.
So I think the structure is for one sequence, and but the MSA has different graphical sequences.
Yeah, so what's really happening is it takes the single representation into the recycle as well. So what the single representation is actually what's being added to the MSA. I don't think there's any information coming from the predicted structure that goes back into the MSA representation. But the previous pair representation after the processing and the structure both come in and update the initial pair representation.
So in the refined MSA, why can't we remove all the sequences except the query?
Because we're making the single structure. So in the end, we want a single structure representing our query sequence. So these other sequences just aren't really important anymore. So ideally, we've got all the information we can out of them at this point. And that everything we need should be in the single representation is kind of the idea. So we're just we have all this information, we're just trying to summarize it into the single representation and then use that for the final prediction so you get the 3D structure.
Templates, right? So the C stands for number of
Channels. It's just,
Okay.
that's the vector dimension.
So for the MSA, we are extracting basically one the representation corresponding to one sequence.
Yes.
Yes, and for the pair representation, so basically the contact or the distance map, right? You said we have 4 templates or something.
Yeah, so they combine all those 4 templates into a single pair representation.
Okay, but at which stage?
Uh,
The first one.
It's in this line. There's an embedding step that happens between the raw template information into the pair representation. We'll go over that in a few slides, what that actually means. But they essentially, in this blue arrow, convert the raw 3D structural information of the templates into some vectorized matrix here. Any other questions?
One last question.
Yep.
So
I know AlphaFold2 keeping 5 structures.
Yes.
How does it keep those other 4?
So I said it trained 5, DeepMind trained 5 different versions of AlphaFold. Each of them are slightly different or use slightly different pieces of information. So the last 3, for example, don't use any template information. They also change like the number of sequences are in the MSA and some other like hyperparameter stuff. So technically they have 5 different versions of the models. They all perform fairly similar, but they all give slightly different versions of the 3D structure, which it's hard to say exactly, but then they like use the predicted confidences to rank those 5 models that were produced to get their like final predicted structure.
So is there a way, well, why would anyone use the second or the third or the fourth or the fifth model compared to the highest confidence?
I think most people just use the highest confidence.
Okay.
It's just it's hard to say what the highest confidence, which of the 5 models will produce the best structure a priori. It's hard to say that a priori. So you have to make those predictions and then you rank them based on their confidences. And then you typically use like the best.
Yeah, if I could add something, I know a lot of people trying to design conformational switching proteins. One filtering threshold that they'll use is having say, 1.5 angstrom RMSD to both design states by any one of the 5 models. So one filtering metric that people will use is predicting with all 5 models and seeing whether 3 models are predicting one of the conformations and 2 the other. And actually, one other note about the MSA diversity, people have been able to get alternate conformations of natural proteins by clustering sequences in MSAs by similarity or by family, and that will sometimes yield or maybe the covariance will be stronger in certain positions for a certain subfamily, and that will have a stronger indication for contacts in one conformation, while a cluster of sequences may encode another conformation. So, sort of playing around with MSA depth and diversity yields different predicted conformations too.
Yeah.
If the MSA is so important, why do people use it as a validation step for de novo design?
What do you mean by validation step?
So whenever people kind of like string together a design pipeline, Arc Fusion, MPNN, AlphaFold, and then compare.
Yeah.
Why even do AlphaFold if it's predicated basically entirely on the MSA? And like you said in the beginning, that de novo designs don't really align to anything in nature.
Yeah, so that's a good point. Why even use AlphaFold if there's no MSA information for these de novo proteins? It's interesting that AlphaFolds can still predict these de novo proteins pretty good in some cases. In some other cases, it's just completely wrong. But I don't really entirely know why it's able to do some of them. Maybe some of the sequence patterns in these de novo proteins are so strongly pointing towards a specific topology of the protein that it's just easy to pick up those signals in the sequence. I think that's probably why a lot of that happens, because a lot of the de novo proteins are just super hyperstable. It's typically smaller too. And so it should be easier to pick up on those structural patterns in those sequences than maybe something that's highly flexible. So I think that's where some of it comes from. Let's keep going then. Okay, so like I said, there's that kind of hidden step, converting the raw data into the actual vectors that we use for the structure prediction. So this is that embedding step. This is kind of what was hidden in those blue arrows. So essentially, there's actually another step that is obscured. Sorry, but yeah. So there's a bunch of features that they extract from this raw data. For example, they take the residue index, so which position in the sequence is this amino acid? This is, remember, residues long, as you can imagine. They have this target feature, which is a number of residues by feature dimension. This feature is essentially combining a bunch of information about what residue type it is, as well as some information, I think it's actually just amino acid type. So you take the amino acid type and then you convert it into a vector by making it a one-hop vector. So essentially we have 20 amino acid types we make a vector that has 20 spaces in it. We set them all to 0, and then we have we put a 1 in whichever dimension is the one representing the amino acid that we are. So if we have a 20-dimensional vector and we have alanine, that's probably the first one. So you just put a 1 in the first one. So that's kind of what they're doing for this featureization. The MSA, they take a bunch of features like profile information, so like bring it into a single value. They also include like how many deletions are next to each other and stuff like that. So it just really tries to capture what this MSA looks like. There's template angle features. So these we have the actual structures for. So they take some angle features like the dihedral angles of the backbone and throw that in here, as well as some pair information. So this includes like the histogram of carbon betas, or I think it also includes some pair angle features. I can't remember. Sorry. But yeah, they form all these initial feature vectors from the raw data. So they have all this raw data essentially coming from the model, or from the raw information, the MSA and the templates and the sequence itself. They do a bunch of operations to convert it into the MSA representation and the pair representation. So what they essentially do is take this residue index and then compare each pair of residues, where they are in the sequence relative to one another. They use that as part of the pair representation. They also use the sequence information from the query sequence in the pair representation. For the MSA, they incorporate the sequence information as well as the information coming from the MSA itself. They concatenate those, or just add those together after doing some operations on them. They actually limit the number of sequences in the MSA, but some proteins have a lot more sequences than what they set it to. So they include this extra MSA features, where they take all those extra sequences that they had and compress that into another set of information to add into the pair representation later, because there's this extra MSA stack. So they try to just use all the information they have. If they had a large MSA, they want to take information they can from that. These template features are modified and then added to the pair representation, just to try to extract information about where these residues are relative to one another in 3D space, and they add that to the representation that's kind of form the structural hypothesis that gets evolved throughout the model. And then these are the inputs into the EvoFormer, which we'll talk about. Any questions? Yeah.
It's okay if you can't. Talk more about how they add the features together, just like I mentioned, Randolph.
Yeah, so it kind of happens after converting the features into these the channels dimensions. So like this, I said, is maybe 20 dimensions. I think it's like 23 or something like that. But they they do a linear projection on that essentially and convert it into a higher dimensional representation. And then that higher dimensional representation is the same for all these. So you can see this is going to CM. This also goes to CM. These go to CZ, which are for the pair representation. This comes out as CZ. This is CM, and then this is CE, which is just the extra stuff. So what they do is take this information that is of different dimensions and then project it into a higher dimensional space that is all the same. And then they're able to add those together pretty simply. The next section requires some knowledge about attention. So I wanted to show this video that I think is really excellent. And yeah, so this is a video by 3 Blue 1 Brown, sorry. And he does a great series on deep learning if you're interested, and the visualizations are excellent. But I wanted to show this small snippet of this video that kind of tries to break down what's going on inside a large language model, which really uses attention to process all of its information, which is the same mechanism that AlphaFold uses to process its information. Although it's maybe slightly different, and I'll explain those differences. But I think this will give you a nice overview of what it looks like.
Kick things off with a very high-level preview of how data flows through a transformer. We will spend much more time motivating and interpreting and expanding on the details of each step, but in broad strokes, when one of these chatbots generates a given word, here's what's going on under the hood. First, the input is broken up into a bunch of little pieces. These pieces are called tokens, and in the case of text, these tend to be words or little pieces of words or other common character combinations. If images or sound are involved, then tokens could be little patches of that image or little chunks of that sound. Each one of these tokens is then associated with a vector, meaning some list of numbers, which is meant to somehow encode the meaning of that piece. If you think of these vectors as giving coordinates in some very high dimensional space, words with similar meanings tend to land on vectors that are close to each other in that space. This sequence of vectors then passes through an operation that's known as an attention block, and this allows the vectors to talk to each other and pass information back and forth to update their values. For example, the meaning of the word model in the phrase a machine learning model is different from its meaning in the phrase a fashion model. The attention block is what's responsible for figuring out which words in the context are relevant to updating the meanings of which other words, and how exactly those meanings should be updated. And again, whenever I use the word meaning, this is somehow entirely encoded in the entries of those vectors. After that, these vectors pass through a different kind of operation, and depending on the source that you're reading, this will be referred to as a multi-layer perceptron or maybe a feed-forward layer. And here, the vectors don't talk to each other. They all go through the same operation in parallel. And while this block is a little bit harder to interpret, later on we'll talk about how this step is a little bit like asking a long list of questions about each vector, and then updating them based on the answers to those questions. All of the operations in both of these blocks look like a giant pile of matrix multiplications. And our primary job is going to be to understand how to read the underlying matrices. I'm glossing over some details about some normalization steps that happen in between, but this is, after all, a high-level preview. After that, the process essentially repeats. You go back and forth between attention blocks and multi-layer perceptron blocks, until at the very end, the hope is that all of the essential meaning of the passage has somehow been baked into the very last vector in the sequence. We then perform a certain operation on that last vector that produces a probability distribution over all possible tokens, all possible little chunks of text that might come next. And
okay, that's pretty much most of what I wanted to show. But I want to take what they just talked about and kind of put it into the protein world of like what we're working with AlphaFold. So they mentioned these tokens, these small chunks of text or video or whatever. In our case, these tokens are individual residues, right? Like they're this discrete object within the protein. They need to all talk to each other, which is how the attention mechanism allows them to talk to one another. But it isn't restricted to like a local space in the sequence, which if you remember when I was doing the CAS thing, I was talking about these convolutional neural networks. So these are very local in structure, or in sequence, sorry. So each residue can only talk to its nearest, 16 neighbors. It kind of depends on the filter you're using. But you're restricted the range of communication between each residue in a convolutional neural network. In attention, we're talking to literally every residue. So every residue can talk to one another to figure out if we should be near each other, if we should be far each other, if we need more time to figure that out. There's a lot that can go on in between in these attention, and then they're updated constantly. So they're constantly talking to each other to come up with a better hypothesis of where they should end up being. And that's kind of how the attention mechanism works. That's the high-level overview of it. Like practically what we're doing is each token is creating a query and a key and some values. Essentially, these are just, you can think of it as like a lock, so or a safe. So we have a key, a certain key that would unlock that safe, and in that safe is a value. What we're doing is we're comparing each token's query to every other token's value to see how much they agree. If they agree, then we're going to take that value and use it. If they don't agree much, we're not going to really care about that value. So really what we're doing is taking two residues, creating a bunch of information about them, and then comparing them, seeing what agrees, what doesn't agree, and then propagating that information forward. What's also happening is there's a bunch of different heads, so these can all pay attention to different things. So I think one analogy that I like is like thinking of this like a dating app, where each person has a variety of different aspects to their personality, maybe the type of music they like, what they like to do in their free time, stuff like that. you have a variety of different things in each of those categories. So maybe you like jazz music, maybe you like blues, maybe you like to draw or paint or whatever in your free time. So we take all of those different properties and then compare them to one another. So maybe you're find somebody, see how well you match with somebody else on the app. You would compare yourself to that, and then that's how you would kind of get a compatibility score, a similarity score, some sort of measure of how much you guys are matched together. This is kind of similar to what's happening here. We're trying to look at how much these residues should be paying attention to each other, how much they should be talking, and that the heads just allows you to express different aspects of that. So maybe the music type, the hobbies, etc. Okay. If you can, please open up the slides. There's this interactive notebook. You shouldn't have to blend anything in there, but I think it's a fun way to like visualize some of the attention connectivity within a language model. So you can start looking at two sentences and then comparing what each word is looking at within those sentences, within each block of attention too, because there's a video wants attention. So spend maybe let's spend 10 minutes looking at these. And then I want to talk to you guys and see if you come up with any like unique findings that you see inside of this network. So, like I said, attention does kind of form the backbone of most of the operations that they do in the EvoFormer as well as the structure module, as we'll see later. But they don't necessarily do it in the same way as traditional attention. So in traditional self-attention, maybe every residue, every token is looking at every other token. But here we have these gigantic vectors, these matrices of vectors that would be really difficult to do if you had every position look at every other position. Because that would be S times R squared, number of like attention operations. So what they do is also enforce some inductive biases, some prior knowledge into the architecture itself to help it learn maybe something useful. So what they do is they apply row-wise gated attention. So what this does is each row in the MSA is a sequence, right? It comes from different species, but it's a sequence. So what this tries to capture is the information in that sequence. What does the sequence mean? What does it represent? Why are these tokens the way they are? Like what specific patterns are in that sequence and why they're there? And they do that on a sequence level. So each sequence looks at its own residues and then tries to understand them. And then it updates its own state based on what's in its sequence. And then they do column-wise attention. So now they look at, for every position, looks at all the other residues, all the other sequences at that same position. So the first residue coming from a human sequence looks at the first residue coming from the fish sequence. And they do that all the way down the column. So this starts to get in that evolutionary history. So is this residue changing? Is it conserved all the way throughout the evolutionary history? Does it switch suddenly? Are there only two preferences? There's a lot of interesting things that can come out of that maybe. And then they do a transition. So after it's been updated based on its sequence, then updated based on its evolutionary history, it just updates itself. It does like what they said in the video. It kind of asks a bunch of questions and then maybe updates its own states. So that's really the processing of the MSA. And actually in here, they also apply the pair representation into the MSA, or into this attention. So it's a way of just kind of like incorporating the pair information into the MSA so that these two representations can talk to each other. So we don't want them to come up with different hypotheses. And then after we've updated the MSA representation, we add that back to the pair representation using this specific function. I'm not going to talk about what that means. And then they do some processing of the pair representation. So the pair representation starts to talk to itself and try to come up with a structural hypothesis of where everything needs to be. And here they use some very interesting operations called triangle operations. So they have a triangle update, which we'll talk about on the next slide. And then they have this triangle attention, which we'll also talk about on the next slide. But the idea is to enforce more inductive biases into the model itself. Any questions about general EvoFormer?
Sorry, what does the plus circle mean? I just like haven't read these terms.
Oh, that just means added.
Oh, maybe
You just add the representation. Yeah, so this is just a skip connection. So you take the previous input, compute like an update to it,
Oh,
and then you add it to it. So it's kind of like computing a residual and then adding that residual to it. Yeah. Okay. So the triangle steps are very interesting, and the main inductive bias that it kind of tries to enforce is that three residues. So these proteins are objects in three-dimensional space. So they obey physical constraints based on that space that it lives in. For example, the triangle inequality. So the two sides of the triangle cannot be greater than the sum of the two sides of the triangle cannot be greater than the other one. So what they do is enforce that by letting triplets of residues talk to each other. So we have residues I, J, and K. We have their pair representation here. So IJ, JI, KI, IK. And they connect them all based on this, so you can form all the different connections. And then they use different edges of that to update each other. So they let these two edges combine information and talk to this guy. They combine the outgoing information, these vectors going in the opposite direction, and allow it to talk to that guy. So that's kind of what they're doing. And then here they're looking at all the different triplets and then combining it into the pair representation. So this guy talks to this guy, this guy talks to this guy. So we'll take that vector and combine it into this information here. So it's really trying to connect three residues and get that information from that third guy into this because they kind of try to obey that physical constraint. So the idea is really just we're updating a pair position. So these two residues have some sort of interaction between each other. That's what this represents. But that interaction depends also on where these other residues are. So we have to try to get that information also into this pair representation and update itself too.
Can you explain these particular steps, outgoing edges, incoming edges, and so on?
Yeah. So there's like these two different directions. Like you can go from K to I or from I to K. And so if both of these guys, so this is from I to K, and this is from J to K. Both of these guys are going here, and since they're both going outgoing of the two nodes, so these are both coming out of the nodes, we combine those into this pair representation. And then the incoming, these are the two nodes that we're trying to update, the coupling between those that we're trying to update. The third guy is sending information from this pair and this pair, and then we want to get that information into the pair.
I'm wondering what's the difference between the triangle updates and the triangle self-attention?
Yeah, so it's essentially combines more information into it. It's also more expensive and more computationally more computationally expensive. They say that they originally came up with the multiplication, triangle multiplication, as a cheaper, simpler alternative to the triangle attention. But they found that incorporating both of them was better than one or the other. So that's why they have both.
We're doing all of this for the objective of making sure that IK plus IJ is greater than or equal to K.
We're not like telling it that's our goal. We're just allowing all these guys to talk to each other, which should, like, in the end, the model needs to obey those constraints, right? Like the atomic structure needs to obey those constraints. But in order to kind of get it to start thinking about those constraints, it needs to open that door for communication between that third residue. It needs to start thinking about that other residue and where it is in order to start actually forming that structure.
So these constraints are checked in the structure module then?
No. They don't like enforce that constraint.
Okay.
It's just a way of opening the door for communication. So you're not going to think about that third residue without like explicitly adding it to this triangle. Like this, so these pairs residues are thinking about themselves, right? And they've got some idea of what is around them because of the other attention operations. But this representation between, so this coupling between residues is not actively thinking about that one until we open the door and allow it to communicate with those other couplings.
I think the way it works is it kind of creates a path of least resistance. So like, if I give you data and I tell you need to find patterns for how this data works, so like how do these atoms interact? and then you don't give it a way to start thinking about it, it's gonna take longer to kind of get to that conclusion. It might or might not find that conclusion. But once you set up the operation, like Nick is saying, it's like, oh, this is an option. Oh, this works really well. I'm converging really well. This is really good. And then it just starts automatically incorporating that physicality.
Yeah, I think maybe in this conversation, there's one missing link, which is in the next slide, because I looked at it. But in the structure module, ultimately, you're predicting the residue frames. And when you finally output residue frames, inevitably, they're going to satisfy the triangle inequality. Here, I think this is an example of an inductive bias, where a priori you know that the outputs should satisfy the triangle inequality. And so it makes the model more efficient, and then it simplifies the objective for it if you explicitly, in these triangle updates, enforce that the model is passing information between, triplets of points, so that, it may choose to leverage that information to, ultimately make more accurate predictions after updating each residue's representation by other pairs of residues. Okay.
Yeah, it's all very kind of like abstract and hand wavy, I know, and I'm sorry, but I think one compelling evidence of why, to even include this is one of the ablation studies. They in the ablation studies, they removed this and saw the effect of not having this triangle attention, and it actually made it worse. So I think it really is just giving it another option, and whether the model takes it or not, it doesn't have to. But if it learns to take it and use it efficiently, it can maybe be even more efficient than without it. Or it would take less time to train, or some other properties like that. Yeah, that's my intuition.
Going back to this question about if AlphaFold tries to predict a sequence that is intrinsically disordered protein and it spits out spaghetti, how does spaghetti protein still satisfy this property? Right?
Well, it'll satisfy the triangle inequality just because it lives in 3D space.
Really can't not.
Yeah, it's just kind of the property Euclidean 3D space. It just has to satisfy it.
Okay.
And it's not required for you to fully understand this. It's just kind of give you an intuition of why they've done some of the things they've done inside these models. Okay. So we've gone through the EvoFormer. We've got an updated representation of the pairs, so we know a decent structural hypothesis of what each residue thinks about one another. We also have a nice representation of the MSA, so we've tried to extract all the evolutionary history, all of the information about the covariance, all the structure of each sequence into the main sequence, because remember, we throw away all the other sequences. So now we have the initial single representation, and we have our pair representation. Those just came from the EvoFormer. Now we need to start someplace with the structure. So they start at what they call a black hole initialization. So essentially they have these residue frames and they throw them all to 0, 0, 0. So every residue starts at 0, 0, 0, and then they get moved around, they get expanded, which is why when we saw that video, everything was just kind of collapsed on each other at the very start of the video, and then they kind of expanded out. That's because of this black hole initialization. So the positions of each residue, which are represented by the frames, I'll talk about the frames in a few slides. Maybe the next slide, I don't remember. But these just represent where the residues are in 3D space, essentially right now. And then we have these representation of the sequence and then each residue pair. They go through this IPA module, which just very high level allows each of these objects to talk to each other. And then they use that updated states. So each of the guys talk to each other, update themselves, get a new idea of who they are and what they mean in context with these other guys. And then they take that representation and use it to update the positions. So now they've taken the information from the pair representation, the single representation, and the current backbone location. And then they predict an update to that backbone location. So now we need to move out because we're all collapsed. That's not good. We take that, and then we take the updated positions, and now we predict where the side chains should be, because we don't really know where those are yet. Most of the time, it's going to be really bad at start, because we haven't done a lot of processing. But this goes through 8 blocks of this iterative update. So we all start at the center, and then it gradually grows out, and then into these secondary structural units that you know of. And now we have a fully predicted structure with all heavy atoms, since we predicted our chi angles, and then use those to place the sidechain atoms. Yeah.
So the backbone frame is basically carbon, no carbon, alpha carbon, and nitrogen, or something like that.
It's carbon alpha, it's nitrogen, carbon, alpha, carbon.
Yes.
Yeah.
Okay. So basically, by definition, these bonds and the planar bond are restricted, right? By definition. But since the translations between the backbone frames are not, so the peptide bond is not restricted, and it can be illegal.
Yeah.
Illegal, let's say. Can be nonsensical.
Exactly. So that's what I briefly alluded to that when I said that they can move independently. So that breaks the chain structure of the polypeptide, and then they're able to simultaneously refine each other. And most of the time, it does pretty good about keeping that constraint there. But when it needs to, it will break it and then refine it back into place. At the end, there's also an amber relaxation step that they do. So they throw it through the amber force field to enforce these chemical constraints. So that's how they make sure that it's chemically valid at the very, very end. But in the model doesn't have to produce something that's chemically valid, but it tends to.
So yeah, but the force field will eliminate any excluded volume violation, right?
It's really constrained to the input structure. So so they heavily constrain the force field based on the predicted structure, but it does fix some of the bond geometries.
Earlier, someone asked whether there was a way to tell the model to use the template information more than it already does. And one way that people have come up with is, instead of black hole initialization, you can initialize from a template structure, and that may sort of over predict that template structure, but that's one way that it can use that information more. And presumably, if you initialize from your template and then ran similar cycles, the model may substantially deviate from that initialized structure.
Yeah, but you have to be kind of confident in your template in order to do that, right? You don't want to use a template and it just be the wrong one, and now you're overly biased towards that confirmation. So Rosetta-Fold2 actually includes essentially that. They initialize their coordinates based on their templates.
And could you use this template only certain parts of it and do it many times? So
Yeah, so you can technically. Out of the box, I don't think you can. You would have to go in and mask some things. But you definitely can restrict the information that's going into the model. That's pretty easy to do. So we've talked about the structure module. The next step I want to talk about is the IPA, what's kind of happening, and how these 3 objects are talking to each other. But before I do that, I want to take a slide to talk about SE3, which is a manifold, which is just a space you can think about that's very locally Euclidean, so it kind of looks flat. But the main idea is that we have these residue frames, which are objects in SE3. So these frames literally represent a coordinate axes. So you have 3 orthogonal vectors that represent a frame, 3 different directions. And it's an object of SE3 because you can parameterize this using a rotation matrix and a translation. So that is really what defines SE3. You have a rotation matrix and translation, and you can move that object around in 3D space by rotating it or translating it. And this kind of knuckle here is where the translation kind of comes in. These objects in SE3, protein, if you decompose it into a bunch of frames, is an object of SE3. There's some symmetries that we need to keep in mind. The main idea is that if you rotate or translate your proteins, we have this protein. If we rotate it and move it around in space, it's not changing the protein. It's the same exact protein. So technically, the fact that it's a protein is invariant to the global transformation. So no matter where we move it, it's still a protein. That's called invariance. Formally, if you apply a transformation to an object and throw it through a function, It does not change the output of that function. Now, the coordinates, however, are not invariant. Because we've now moved our protein, the coordinates are all changed, right? We've rotated or translated it, the coordinates are moving around all over the place, and they're not the same. But they move in a very well-defined manner. Like, we can easily calculate where they are now based on this transformation. So we say that the coordinates themselves are equivariants or equivariants to the global transformation. So mathematically, if you apply a transformation to an object and throw it through a function, there is a unique, I don't know if it's unique, but there is another transformation on the other side that you can apply. Okay, questions on that? So these are just kind of two properties to keep in mind when working and modeling with proteins. A lot of the time, people try to bake these inductive biases of invariance or equivariance into the models themselves. AlphaFold, for example, uses invariance, whereas Rosetta Fold uses equivariance. And they do it in a different architectural stance, a different architectural way. There's these different blocks that they use in their structure module that preserve the equivariance aspect of the features that are going through the model. Yeah, I can answer more questions if you have them. But I just really want to highlight that these properties are important when thinking about proteins because like the sequence isn't changing when you rotate it, so that property is invariant, but the coordinates are. The dihedral angles are not changing, but the vectors of like the center of a helix will change.
Like, wouldn't it be possible to also integrate like internal coordinates with directional coordinates because that by definition it would fulfill this criteria and reduce the degrees of freedom prediction. And
So
it's possible why it doesn't anyone do this.
I think one of the, let me just, there's this diffusion model on torsional space for proteins from Microsoft. So here they're parameterizing the diffusion space over torsional angles. It's really hard to do. And there's a lot of reasons why. The easiest, I think, to grasp is this lever arm effect. So if we have this protein here, and we change the bond, the torsional angle here, we have a dramatic change in where these residues are. This is the lever arm effect. You want to be able to refine the local structure without changing something that's really far away. So when making this rotation, you also have to make compensatory rotations around these other bonds in order to make sure that these guys really far away don't move. You see, towards the end, it gets really protein-esque, but now it's making a lot of minor movements to make sure that it doesn't break that structure. Okay.
There's one thing I want to add for the idea of equivariance and variance is that generally a lot of times you'll hear it be talked about, it'll be in terms of the architectural components. However, these properties are not limited to architecture. The task can be equivariant or invariant, the items that you're looking at. So these words can be used for a lot of different things. And when you put the whole thing together, the task and the properties and the data and everything that you're putting in, you have to be very careful about each component so that tuning doesn't break.
So I mentioned that AlphaFold uses invariance here, is where they use it. This invariant point attention, which they've created for this model, they call it IPA. And it's a way of allowing the pair representation, that single representation, and the backbone frames where they are currently located to talk to each other. And essentially, the single representation is creating some queries and keys and comparing them to the 3D positions and trying to figure out which residues should talk to each other and move around relative based on where they currently are. It's also looking at everything in the sequence space. So like it's making queries and keys based on the sequence information alone. So it knows which residues it should talk to just based on the sequence. The pair representation is being used to update that because the pair representation has some sort of structural hypothesis of where the protein what the protein should look like. So it's used that to update these attention affinities. So which residues it should pay attention to based on the structural hypothesis of what the pair representation has. These get updated and create attention weights. So now each residue knows how much to pay attention to which other residue, and then they update the single representation. So essentially, pair representation, the single representation, and the backbone frames all combine information. They look at each other. They get biased by what the structural hypothesis in this pair representation are. They know where they are in relative space. And then they update that single representation, which is just this vector of number of residues by channels. So we're taking all this information and throwing it back into the sequence representation. And then, was there a question? Yeah.
So when during recycling, does it go to IPA again?
Yep. So this IPA is a part of the structure module, and there are 8 blocks of this. So it goes through this one time and then 7 other times. And this representation keeps getting updated. After it gets updated from IPA, it's used to update the current positions of the backbone frames, which then get used to update the sidechain locations. So every time it goes through the structure module, it moves them, and it moves them 8 different times, and then that's your final structure that gets recycled, and then it goes again. So every recycle, everything starts at the black hole initialization, they get expanded out, that structure gets featureized and thrown back into the model to try again. So this algorithm here is just how they use the information from the recycling. You don't have to fully understand it, but they essentially take the information from the predicted coordinates. This is the C beta location, or C alpha if it's a glycine. And they take it and they bin it, so they create a one-hop representation based on a bunch of these distances. And then they project it into some high-dimensional space, and then they essentially add that back to the EvoFormer, the representation that came out of the EvoFormer. Sorry, no, my bad. They have that pair representation that came out of the EvoFormer. They combine that with the distance information from the predicted structure itself. So now we have an even better structural hypothesis of what this protein is supposed to look like. We also take that single representation and normalize it to output it, and then both of these get added to the initial raw featureization to go for the second pass, the next pass. Okay, so I guess this is where I talk about the residue gas. Maybe should have been earlier, but essentially each residue is a frame, which is really defined by their N-C alpha C bond. So the N-C alpha C is kind of what I was trying to represent with my hand. And then the carbon beta, I guess, would be like over there. But it forms, so this is a well-defined plane because it's these are planar. And then we can compute the normal vector to that plane, and that will help define that residue frame. And so now each residue is this disconnected like triangle object, this frame that can move around in 3D space. We also are parameterizing the side chains in terms of these chi angles. So you see these like little green arrows that kind of spin around the bond. And that's kind of what the chi angles are representing. You take everything past that and spin it, which is changing the chi angle. And some of these side chains have more chi angles, so there's more things to rotate. But that's essentially what the proteins look like when it's going through AlphaFold. And essentially, in the end, hopefully these will be close enough to actually make a peptide bond. Not always the case, but hopefully. Okay. Because we're parameterizing everything in the terms of frames, there's not like a super good loss function for that. Not many people I'm not aware of any other paper that used frames before AlphaFold. There probably is, but I'm not aware of it. So they came up with this new loss function to help take into account this representation, but it also provides a lot of other benefits besides just working with this representation. And I'm not going to spend much time on that, but we can talk about it if you want. But this loss function is kind of represented by this diagram. So we have a true structure represented by the green kind of curve here. And we have our predicted structure, which is this gray curve. You can see it's slightly off. But what they do is this frame aligned point error. So what they do is they take every frame, so every residue, and align it to the native position. And then calculate the error of every other point within a certain neighborhood. So this is kind of like a measure of local structural similarity, if you can imagine that. So we've aligned that residue we're interested in, and now you can see that there's a little bit of error here, there's a little bit of error here, there's a little bit of error here, and it's trying to minimize all those errors. We're trying to push these guys closer to try to minimize that. And so what the effect is, this guy will be moved, but also once we get to this residue will be aligned to this its corresponding residue, and then there will be error over here. So it's simultaneously optimizing each local environment, which is very beneficial. It also allows cool properties like chirality and stuff like that too. Questions about FAPE?
The FAPE loss is so important, or why this is a much better loss than something like RMSD?
Yeah, so, well, property-wise, RMSD is, I don't think it can handle chirality. It's like the reflection aspect of it. I don't think it can capture that, whereas this could. I think it also has different metric properties. I don't have a great.
It's also lower in memory usage, so for RMSD you would need like the level of respondent detail. Here it just decomposes to just the alpha translation and then a 3x3 rotation matrix. So it's a lot fewer parameters that you need to have for the whole thing. Chirality is a really big thing. Yeah.
And there's a generalization of this one too. It's FAPE, but I'm not.
I guess at what point of the process do the frames get converted into like the more like its molecular equivalent, like with the carbons and like nitrogens and oxygens in place?
So that's only really happens at the very end.
Okay.
So they're represented as these frames throughout most of the module itself, and then they're able to represent the side chains in terms of those chi angles, those dihedral angles, and essentially that represents a residue. The combination of that rigid frame and those chi angles are what defines a residue's location.
Okay.
And then when they're ready to output a structure, they do some transformations into make that a each atom's coordinates.
Okay.
So there's like a some idealized coordinates you can make based on idealized bond lengths and angles. Essentially, you can align that, and then you take the torsional angles, and you could take frames and like make a tree shape off of that. This is essentially how they do it. This is the loss function that they use. There's two different stages of AlphaFold. I kind of hinted towards that when I mentioned the self-distillation step, because that's kind of in the fine-tuning step. Actually, is it in the regular training? I don't remember. Sorry. But anyway, there's two stages. The second one just introduces some extra losses for structural violations. So they do kind of enforce it during fine-tuning, but the initial tuning is kind of just get the overall structure right. So there's multiple components. I mentioned FAPE, so this is making sure that each residue's frame is aligned with the frame in the natural protein. They also have this auxiliary loss term, which is a FAPE, but only operates on C alpha, and it has a chi MC. And I think this is pretty important because when we look at the structure module, this is kind of where the auxiliary loss is being enforced. So it goes through the structure module. We have an updated residue frame. We have the updated chi angles. And now we compute a loss. How far are these off from the native? They're going to be pretty far off compared to the last stage, right? Because the last stage will have a lot more compute. We'll have a lot more time to update it, get into the correct positions. So these are going to be pretty wrong. But they enforce a loss nonetheless. And so by doing that, they kind of allow the model to make iterative refinement, right? You want each module to decrease that loss more and more. Whereas if you just enforce it at the very end, it doesn't really matter what's happening in the middle as long as the end works. But now they're kind of enforcing a funnel-like shape into the model because it's getting better and better representations, and now the loss is getting lower and lower even within each individual block. So I think that's a cool addition. It's also weighted a little differently because there's the chi MC in there as well, so that's just making sure it predicts the right chi angle. There's also a histogram prediction. So what's happening here is I was saying throughout this whole talk that the pair representation was kind of like a structural hypothesis of what the protein should look like. And this is where they really enforce that. So they take that pair representation that they get at the very end, make a prediction of what the histogram is. So they make a prediction of how far away every pair of residues is, and then they enforce a loss on that. So they make sure that that prediction is accurate. And so this is kind of where, why I was saying it has that structural hypothesis, because they're kind of enforcing that with this histogram prediction. They also include this masked MSA prediction, which I think is very interesting, and I think this showed, at least in the ablation studies, that it was quite important for making the model learn about these coevolutionary patterns. And so what they did here was they have this giant MSA with a bunch of sequences from different species. Here they masked different residues from it. So now we're missing maybe this span of residues in the middle of the MSA. And then we asked the model, try to fill that in. What do you think is there? So that gets the model to start thinking about where are the gaps, and then it can also use the information above and below it too, to kind of try to fill in those gaps too. So it allows it to start thinking about missing pieces inside of the MSA, and maybe help refine its structural hypothesis as well. There's a small loss term to make sure that the confidences are learned appropriately, which is important. And then in the fine tuning, they also include a loss to check whether the model thinks this residue is resolved or not, which I think is interesting. It may be part of the reason why it's such a good predictor of disorder. I'm not entirely sure about that, and there's not a lot of talk about that, but I think it's interesting. And then they also enforce a loss just to make sure that the bond angles and bond lengths are kind of appropriate and kind of try to enforce that peptide bond. For the most part, it's able to do that even without the loss, but it just helps enforce it even more during fine-tuning. And when I say fine-tuning, I just mean, so they've already trained a version of the model, they train it even more, but use a very small step size in updating the parameters. So you take smaller steps, but you're able to drive into a deeper minima in the loss function. So in my head, I think of the losses as another way to teach the model about what you want to know. So the masked MSA is teaching it about the coevolutionary information in the MSA. It's trying to fill in the gaps that are missing in the evolutionary history of this protein. The histogram's helping create that structural hypothesis that is iteratively refined throughout the model. The FAPE is, the main one. We want the structure to look good at the end. And then the confidences, we want the model to be have an estimate of its own prediction accuracy. And so that's where the confidences come in. So that, yeah.
Is the experimentally resolved portion of the loss like the P factor or?
It's whether that residue was in the crystal structure or not. Because sometimes in the crystal structures, like you're missing some residues that were unresolved, whether they were disordered or just not part of the, maybe created like a truncation or something like that. That's kind of what that term is checking. Yeah.
So I already know AlphaFold2 is quite quick in the prediction, but if you remove the training loss and then work with the fine tuning loss, because the two losses are essentially the same except two factors, would that speed up the computation?
So it won't speed up your inference. It's not calculating these losses during inference time when you're actually making a prediction. This is only during training time. But the reason why you would maybe not want to include these early, it may lead to very difficult learning process. So if you're telling it to keep all these things in mind while it's making its predictions, it may have a really hard time. But if you remove some of these constraints, then it may be able to find a solution easier, but then you may be able to refine that solution by tuning it even more with the actual losses. So I think the main reason is the training dynamics become unstable when you have a lot of loss terms that can make the learning landscape rugged. So this is essentially defining like a landscape, an energy landscape that you're trying to minimize. By adding more and more terms, you're making it more and more rugged, which is harder to navigate. Cool. So that's pretty much all of AlphaFold2. I want to talk about some limitations though, because it is not a perfect system as all of these systems are. I think one of the biggest ones, one of the most obvious ones is mutations. So if you make a mutation to your query sequence, does the structure change? In nature, probably, right? If you make a mutation to the core residue, you might explode that protein. It may no longer function. It may no longer fold. But since AlphaFold, as we've talked about, relies heavily on the MSA, a lot of the time it just doesn't care if it's slightly different sequence. Because the evolutionary history, within the evolutionary history, the positions change based on the species you're in, based on the coevolution. So if you change like a position in the query sequence, not that big a deal as long as everything else is mostly the same. So it's not really good at predicting the effects of mutations in query sequences. It's also not amazing at novel proteins, although I think it's okay. It could be better, as Ben is working. It's also not great at multiple states, although we've talked about a few ways to bias it, and I'll talk about those in more detail a little bit later. But the 5 models produce different models, although they're usually quite similar. I don't think there's any evidence that they actually represent distinct states, although people are trying to make that more useful. It's also not great at predicting, unstructured regions. Like, it is pretty confident that these regions are unstructured, but it just makes spaghetti. So like you can't really trust anywhere they are at, even though you can be relatively confident they are disordered. It also doesn't explicitly model other molecules, as we talked about. It's only thinking about the protein atoms, but it does, since it was trained on structures from the PDB, it kind of knows that there are other things that it's not thinking about there. As we saw, it was able to coordinate that zinc ion. It's still able to kind of reason about chains that are not there, because it was trained on actual things in the PDB. Yeah.
But with mutations, wouldn't under-relax in a way will encode the mutations in the final step to prediction?
So, Anchor would know a little bit, but it's so heavily constrained towards the predicted structures that it's only really resolving some of the egregious violations, the chemical and physical violations. So it's not going to fix that. Cool. So I want to talk about some extensions. There are a lot of extensions of AlphaFold2 because it was such a prominent example of AI in structural biology. It's also open sourced, so a lot of people have been able to mess around with it and see what they can do. The first one of which came from DeepMind itself. They just expanded it and trained it on multivariate complexes. So they introduced AlphaFold Multimer. They made a few changes to the model itself. Most of them are pretty minor. They took into account some losses to make sure that the permutation symmetry of the chains is accounted for. So the main idea there is if you have like a trimer, you have 3 chains, but the order of the chains doesn't really matter. It doesn't really matter if you call this guy A or C or B. They're all the same chain. So it just makes sure that that symmetry is enforced in the model itself. They also pair the MSA alignments for cross-chain genetics. So if you do search the MSA and you know what species these sequences came from, you can pair them together, which may provide some extra information about how they actually interact. Because if this mutation, there's a mutation over here that's compensated by something over here, maybe those 2 regions are in contact. They also introduced a new way of subsetting the residues. So essentially, they can't train on full proteins, so they train on portions of the protein. Usually there's still pretty large portions, like 356 residues or something, 256 residues, and then 512 residues. So there's still a lot of protein. But when they were cropping it with monomers, it doesn't really matter how they crop it. Or it does, but not that much. But for the multimers, they crop it specifically to account for the interface between the proteins themselves. And then they have some various other small changes. But I think the main sell point for AlphaFold Multimer is that it is much better at .q. .q score is really just a measure of the docking quality between 2 proteins. It is much better than the modifications people have made on the monomer version of AlphaFold. So AlphaFold linker, the idea there is you take 2 proteins, then you insert a super long glycine linker between them, and then those are essentially just now super far away and it can still do a multivariate prediction. It works. It's not as good as Multimer. This gap is very similar. They just add a residue gap between them. And then they compared it to some other methods, but yeah. AlphaFold multiplier exists and it's better than some of these other guys at multiplier prediction. As you guys most probably know, there's a structural database now of a bunch of sequences. There's over 2 million entries that cover most of uniprotes. And they include the entire human proteome as well as 47 other species proteomes. So they've taken a bunch of sequences and made a bunch of predictions. One of the limitations of this is that it's only monomers. So if you have one multimeric structure from this, you can't get it, unfortunately, but yeah, this is still a really nice resource. This is a cool extension that I, from Walner, that really like gets to the idea that AlphaFold knows what a good structure is. It just may need a lot of help getting there. So what Walner did was they introduced, they turned on dropout, which is just the idea of turning off some of the information, some of the signals passing through the network, which just enables it to be more random, essentially. And by doing this, they were able to get more diversity into structures. They enabled more recycling, so it gave it a lot more time to refine that structure. And by doing so, you're able to get a lot of diversity, and a lot more structures. And eventually, if you like rank them based on their confidences, you can find that these structures are actually much better than just the single AlphaFold multiplier prediction. But there's a massive caveat. You need to do a large scale prediction with these because you get a lot of diversity and then you have to rank them. So you have to do like probably 1,000 times more compute. So it's really inefficient to do this, but it kind of points to the fact that AlphaFold kind of knows what it wants out of these proteins, even though it might not get there in that limited amount of compute. We also see evidence of this in AlphaFold3. AF cluster is a method from Sergei Ovchinnikov and some others, but they help bias the MSA towards predicting different states, as we've kind of talked about throughout the class. By taking the MSA and clustering it based on sequence identity, they were able to bring together sequences that may be biased towards a specific conformation over the other. So here they just show some examples of these fold switch proteins that switch based on the context. I think like one's like a night-day switch or something like that. I don't know exactly. But it's able, with the MSA, it really predicts this FS state. But if you use the closest sequences in the MSA, you can like bias it towards a different state. So maybe there's, so that kind of points to the fact that the MSA is really important and definitely can help bias it towards different states, although like it is also producing other things outside of here that are confident, like this blob here, but may not be an actual physical state. So once again, like these may produce non-realistic states, but you can still get some realistic things out of it too, which is interesting. Also from Ovchinnikov is AF2 Rank, which is a really cool way of assessing the quality of a prediction. So they found that AlphaFold kind of learned a really nice energy function and it knows what a good structure is. And so by using some of its confidence values in a different way, you can rank the structures that you're giving it and know if that's a good decoy or not. So if it's actually a good structure or not for this given sequence. And it's actually really robust at predicting or discriminating between a wrong structure and the right structure, which is really cool. There's also a lot of other things that people are doing, including using AlphaFold in automated workflows that we've talked about. Most of the pipelines use like RF Fusion, ProteinFN, AlphaFold, but you can do it in a more automated fashion. You can literally link them together. For example, EvoPro, Amrita, helped do this, and the idea here is you create like a genetic algorithm of sequences that get adapted and updated based on the scoring function using the AlphaFold predictions. So we take a bunch of sequences, make a structure prediction, score them based on some qualities or different metrics that you're interested in. Maybe you want to keep the conformation the same in bound and unbound states, or you want to make sure that it has high confidence. and then you rank them, you get rid of some and diversify it, and you can keep going around and around until you get a nice optimized set that at least AlphaFold likes, that are good towards your confidence metrics. Bind graph is a really useful, or really new method that performed really well in this protein design competition, where they used AlphaFold multimer, but they back propagated through it to update the sequence. So essentially you give it kind of a noisy sequence to start with, and it'll make a prediction of some structure that's going to be really bad, not very confident, and then they try to change the input sequence to maximize the confidence as well as some other things. So that helps change the sequence to something that AlphaFold likes, essentially. And then they optimize it with some MPN and more predictions, but it's just another workflow, and they've had great success with that. These are just a small subset of the number of large workflows with these, but yeah, I wanted to highlight these. Okay. Any questions?
How did they update the sequence? What's the last one?
They do it with like a back propagation. So they go through, they have like a noisy sequence. It goes through the model, and then we calculate like its confidence in that structure. And generally you want the confidence to be higher than it is. So you compute like a loss that says, hey, be a better confidence. And then it'll send a back propagation signal. So update, send gradients all the way through the model, and then update the input sequence to be more confident.
So you change the sequence in like continuous ways, and after that you
They
bind-
are continuous representations, which is interesting.
and then you pin it.
You can do like an argmax or something like that to get the actual sequence out, but yeah, it's interesting. Yeah.
So yeah, one thing I think that wasn't mentioned, and I wonder why it's not used. It's like, couldn't you just predict flexibility of chain? Because it would just, there are several things that are very easy, just like from the secondary structure prediction, you can assume that loops are in general more flexible. The termini are obviously more flexible, and couldn't you incorporate the data just to reduce the importance of losses on the residues which are more flexible, because you are actually looking at what is predicted with more confidence, and this is just a loop, doesn't matter. So couldn't we incorporate that in the model?
Yeah.
Why?
Yeah, you can imagine regions that are harder to predict, or that like you're not even sure the crystal structure is right about those regions. Maybe they're super flexible or something like that. You can imagine not enforcing the loss there. Like that is technically feasible. Knowing those regions ahead of time is a little difficult. And with the cropping and all that, I don't know how like practical it is. I don't also know how beneficial it would be. But I mean, it's definitely possible.
Well, because in the fragments like loops, where there's very high flexibility, so deviations like fragments device are huge. So
Yeah.
I assume the contributions could be non-negligible.
Yeah, I mean, they're probably going to be a lot, have more error than the more stable regions, like the secondary structure regions. But it should still learn to try to predict them accurately. So, like, they should still know how to create a loop, even if like it's not super confident in the location, which is kind of what it's still kind of learning to do. Like, if you look at most of the structures, the loops are typically less confident, primarily because it's learned that those are more flexible and harder to predict correct. So it does know that, but I don't know what extra benefit you get from not training those residues, enforcing the loss on those residues.